Hello everyone, welcome back. Today I want to show you some higher level torque problems that really demonstrate how my rules here come into play, especially the special rule after number 2 that's dependent on whether or not the system is in equilibrium. And to do that, we're going to use a device called a seesaw, which you can find at a children's playground. Now over here I have my seesaw, here's the plank, I have two nondescript children sitting on it. But one thing I have not drawn is the pivot, which is the device under the seesaw that allows the seesaw to rock back and forth on it. But we're gonna use it in a slightly different manner today. For starters, we're gonna say these two kids are sitting at the very end of the seesaw, and one weighs more than the other. We'll say the kid on the left weighs 358 newtons, and the kid on the right weighs 222 newtons. Now, here is the question. Where do I place the pivot so that these two kids are perfectly balanced? In other words, the seesaw stays horizontal and does not swing one way or the other. Let's start with the obvious. What happens if I put the seesaw at dead center? If the seesaw is 8 meters long, therefore I put it at 4 meters from one side, what's going to happen? Well, obviously, this side is going to rotate downward or counterclockwise because this kid is heavier. In other words, there's more positive torque than negative torque. So our question again is going to be, where should I put the pivot so this does not move at all? Now, one thing that we can say is that the pivot is going to be on which side. If you just said left to center, then you are correct. In other words, if the left side has the stronger force, it must therefore have the shorter radius, where the right side has the weaker force, it's going to have the longer radius. However, we still don't know where this is exactly, and that is going to be the goal. This is one type of problem where my rule system really comes into play. So let's start asking our questions. Number 1, is the system in equilibrium? Well, the answer is yes, because I stated explicitly that this bar will remain horizontal and will not be moving. 2, where is the axis? Now this becomes a very important question. The axis and the pivot are two different things. The pivot's a physical object. The axis for your problem, based on rule number 1 and using our special rule, can be placed anywhere we want. And I'm going to prove that to you today. Also, we can't put it here. We can't put it above the pivot because we don't know where that is. In other words, if I then try to do torques, I have two unknowns, radius 1 and radius 2. They're both unknown. So where do we put it? To try to get this down to one unknown, we're going to put the axis right here, right under the kid on the left. Well, I'll simply call A. I'm going to talk about why I did that in a minute, but for now, let's ask our third question. How many non-zero torques exist? And to help with that, let's put in our table. Well, A is no longer providing a torque. There is no radius. The force is directly on the axis. The kid on the right, which I'll name kid B, is providing a torque, and we know both the force and the radius. So I'm going to put that right here. There is also another non-zero torque here, and it's from the pivot. Again, if the system's in equilibrium, that means all torques and all forces must cancel. If there is this much force downward, that means there must be the exact same amount of force upward, and that is provided by the pivot. 358 plus 222 means the pivot is providing 580 newtons of force upward. I will make the pivot point C. All right, we have our table. Force in B, 222 newtons. Radius, 8 meters. Torque, therefore, is 1776 newton meters. And the torque applied from kid B would be in the negative direction because this would swing clockwise. The torque provided from the pivot would swing around our axis counterclockwise. Now remember, this is an imaginary axis. So torque direction, you're basically pretending that it can swivel here, and this force would make it swing counterclockwise if that was possible. So this one's positive, force, 580 newtons. The torque has to be positive 1776 newton meters because we need a net torque of 0 newton meters because it's in equilibrium. If I do that, I take the torque divided by the force, and I will put our standard torque equation up in the corner here again. That radius would be 3.062 meters. Now I'm being very accurate here for a reason. And if you're following with me on the math with the calculator, you will see why. All right, so this distance is 3.062 meters. While I'm here, the distance to the other side would be 4.938 meters, which is going to come into play in a little bit. All right, so if I put the pivot right here at exactly 3.062 meters away from the left-hand side and put these two children on it, even though they have different weights, this would remain stable. It would be completely horizontal and it would not swing clockwise or counterclockwise. This is how you find out where the pivot is. Now, let me show you something. Now that we have this information, I'm going to start the problem again and prove something to you. I'm going to go through my questions again. 1, is the system in equilibrium? Yes. 2, where is the axis? I'm going to put the axis somewhere else. This time, I'm going to put it all the way in Kid B. I'm going to make a new table for this, and I'm going to keep all the information we found. So axis in new place. I go to question 3. How many non-zero torques exist? I still have 2. However, this time, it is Kid A because we have a force and a radius, and it's the pivot again because we have a force and a radius, only the distances from Kid B, not from Kid A. So we have points A and C. So the force from Kid A, 358 newtons, radius 8 meters. The torque swinging this way around the axis would make the torque positive. So our torque would be a positive 2864 Newton meters. Because again, counterclockwise is positive in the unit circle. Okay, point C is the pivot. The force would be 580 newtons. The torque provided would need to be negative 2864 Newton meters. Because again, then at torque must be 0 Newton meters. Now, if I use our torque equation and I take the 2864 Newton meters divided by 580, I would get a radius of 4.938 meters, which is exactly what I already have here. So in other words, I could have put the axis on Kid B, no problem. In fact, I'm going to take this a step further. I'm going to take the axis this time, and I'm going to put it on the actual pivot, because now we know where it is. Now that we kind of know what we're doing, I'm going to go through this a little quicker. All right, it's in equilibrium. I know where the axis is. And again, we have 2 non-zero torques, A and B. A, B, force from A, 358 newtons, radius for A, 3.062 meters. The torque for A would swing positive, and I would get 1096 Newton meters. Kid B, 222 newtons. Radius, 4.938 meters. This would swing this way, which would be a negative torque. And if I multiply this, I get 1096 Newton meters, which means we have 0 Newton meters of net torque. Let's do one more to really get the point across. I'm going to choose the center of the platform. I'll call this point D. I set up my table. Systems in equilibrium. I'm putting my axis in a new point dead center of the seesaw. Having non-zero torques. Well, this time I have 3. I have Kid A, I have Kid B, and I have the pivot. So I'm going to add another line here, because they all have a perpendicular force and a distance from the axis. Force A, 358 newtons. Radius for A, 4 meters, because again, it's dead center. Force for B would be 222 newtons. Radius for B would be 4 meters, again, because it's on the other side. Force for C, 580 newtons. The radius for C would be this distance right here, which would be 4 meters minus this. It looks like it's a little under 1. And it comes out to 0.938 meters. Okay, let's run down the torque directions real quick. A would swing counterclockwise, so it's positive. B would swing clockwise, so it's negative. C would also swing clockwise, so it is also negative. Torque A would be 1432 Newton meters. Torque B would be negative 888 Newton meters. Torque C would be negative 544 Newton meters. Anyone want to take a guess as to what this would be if I add them all up? Well, if you did it, or you guessed 0 Newton meters, you would be correct. So the reason for this whole exercise is to really hammer down the point that this system works. You can put the axis anywhere you want. Once you know the system is in equilibrium, you can put the axis anywhere you want, and your table, your total net torque, will come to 0. You could put it under Kid A, you could put it under Kid B, you could put it under the actual pivot if you know where it is. You could put it in the center of the platform as long as you know what all the distances are. So the game is going to be, can you place the axis in a place that will benefit you? That is the skill. If you can do that one thing, then most of the higher level torque problems in a first level physics course are going to be cake. And I'm going to show you two of them right now. The first one is generally called the scaffold problem. I also like to call it the window washer problem because it has to do with a device that looks like this. You may have seen this device in movies on skyscrapers where men are going up and down washing windows, and for some reason, action movies, they love to have fights on these things. So I'm going to create a much simpler representation, which looks like this. So let me describe what's going on here. Here is a platform, just a regular straight aluminum platform. I'm going to say the weight of that platform is 100 newtons. So Earth on scaffold is 100 newtons. Here is a man standing 4 meters from the left-hand side. I'm going to say he weighs 700 newtons. The scaffold itself is 10 meters long, and 2 meters from the right-hand side is this guy's lunchbox. I'm going to say the lunchbox is 300 newtons. For those keeping track, this is a total of 1,100 newtons. Now, here is the most common question for these problems. The scaffold is held up on both ends by 2 ropes. 1, 2. The question is, what is the tension in both ropes? So immediately we have a problem. You have 2 unknowns, and that is no good. A lot of people who have not taken a physics class will take a look at this and say, oh, you have 1,100 newtons downward. That means if I split this in half, each one would be 550 newtons. Well, that would be incorrect. The rule is you have to have as much force upward as you do downward. But there's no rule that states that the 2 tensions have to be equal. In fact, they can't be equal to keep this in equilibrium. And I'm going to show you why. Okay, 1, let's go over questions. Is the system in equilibrium? Yes. Flat out saying this is not moving at all. Again, all torques and all forces must cancel. 2, where is the axis? Here's the big question again. Now, unlike the last problem, there's no pivot, there's no hinge. There's nothing that is classically defined as an axis point. However, again, since we know it's in equilibrium, we can place an imaginary axis point anywhere we want, and the net torque will still be 0. Since we have 2 unknowns, the big trick to this problem is taking your axis point and literally just slapping it on one of those unknowns. The reason is if you are going after torque, tension 1 no longer has a radius. Therefore, net torque from this tension is 0. So looking at question number 3, we don't even need to worry about it anymore because now we have how many non-zero torques exist. Well, we have a distance and force to the man, a distance and force to the center of the platform, a distance and force to the toolbox, and a distance and force to tension 2. So let's set up our table and get to work. Force radius equals torque. Okay, so how many non-zero torques do you have? 1, 2, 3, 4. I'll go from left to right. So the first one is the man. Second one is the scaffold. And again, the force is dead center of the scaffold because it is a uniformly distributed mass. The third one's the toolbox right here. And the fourth one is going to be tension 2. As I suggested before, let's chuck in the signs right now. These 3 are all going to swing this clockwise, which would be a negative torque. Tension 2 swings around the axis counterclockwise, which would be a positive torque. We'll do the man first. Force, 700 newtons. Radius, 4 meters. The scaffold, force, 100 newtons. Radius, 5 meters. Because, again, scaffold is 10 meters long and it's dead center. Force for the toolbox is 300 newtons. And radius would be 10 minus 2, so 8 meters. Force for T2 is unknown, but I know the radius is 10 meters because it's all the way across the scaffold. Let's fill this in. 2,800 newton meters, negative 500 newton meters, negative 2,400 newton meters. Now, all these have to equal 0 newton meters because, again, the system's in equilibrium. The only way that can be true is if the torque from tension 2 is positive 5700 newton meters. Again, I take my torque equation up here, take the torque, divide it by the radius, and I would get 570 newtons. So tension 2 is 570 newtons. So by putting the axis over here on tension 1, we made sure there's only one unknown. Fill in our table, and literally it's like solving a puzzle. You go down this way, must equal 0, then come back and go toward the only thing that's missing. Now to get tension 1, do we have to do all this again? No, because remember, all torques must cancel and all forces must cancel. Therefore, if tension 2 is 570 newtons, tension 1 must take care of the rest. There's a total of 1100 newtons downward, therefore there must be a total of 1100 newtons upward. If tension 2 does 570 of it, tension 1 does the rest, which is 530 newtons. Therefore, tension 1 is 530 newtons. Now you have both tensions. They are not equal, but they total up to 1100 newtons. And again, you can place this axis anywhere you want on the scaffold, and you would still find a net torque of 0. I'd show it to you again, but we don't have that kind of time. Instead, I'm going to show you another type of problem where this technique comes in really handy. And to do this, we're going to use this baby whale. Let's say the zoo wants to find the center of mass of this baby whale. They put the baby whale, which is 6 meters long, on a platform we're going to say has negligible mass. So in other words, we're just going to ignore it. And that mass rests on 2 scales, 1, 2. And the readings on the scales are written in them. 1,352 newtons and 876 newtons, which means the whale is obviously top heavy. And these forces obviously would be directed upward. Now the question is, where is the center of mass of this whale? The whale is not moving, it's being a good boy sitting on this platform. Let's go for our questions. Number 1, is the system in equilibrium? Answer is yes. Number 2, where is the axis? Again, no pivot or hinge or anything like that. So where do we put the axis point? And to help answer that, let's talk about something else. Approximately where is the center of mass of this whale is going to be? Well, it's obviously not going to be dead center because this side is heavier, which means the center of mass is going to be a little to the left of center here. Not sure exactly where, but that is fine. One thing we do know, however, is the total weight of the whale, because it has to be the addition of these 2 scales. And if I add them up, I get 2,228 newtons. We just don't know where this is. So in other words, I can't put the axis here because, again, we would have 2 unknowns. Radius to the left and radius to the right are both unknown. So once again, I'm going to take the axis and slap it all the way over here on the left-hand side. That means I do have a known radius to the other scale at least. 3. How many non-zero torques exist? Well, now I have 2. Radius, force, and radius, force. I'm just missing one of the radii. I will set up my table. Force, radius equals torque. I'm going to have 2 torques. I'll label this A, B, and C, which means force B is producing a torque and force C is producing torque, but force A is not. Again, because there's no radius. This will be for the total, and again, the total torque must be 0 newton meters. All right, so let's go at it. Force from A, 876 newtons. Radius from A, 6 meters. The torque, this would swing around counterclockwise, so that would be positive, which means the force from the weight of the whale, or C, would be a negative torque. So this would be positive 5,256 newton meters. Therefore, the torque provided from the center of mass of the whale would have to be negative 5,256 newton meters. The distance I don't know, but the force I do. 2,228 newtons. And again, I take my torque equation, take the torque, divide by the force, and I would get a distance of 2.36 meters. If the whale is 6 meters long, we predicted it would be more toward the front, which means we should get a distance less than 3 meters, and we did, as anything else would have been a red flag. A little side note, if you go through the math of the center of mass that I introduced back in momentum, you actually come up with the same result. So either technique would actually be good for this problem. However, for torque, understanding that this is possible is actually quite important. Because here's the biggest hint that you need this technique. It looks like you have two unknowns, or you literally do have two unknowns. For the scaffold here, you are missing tension 1 and tension 2. For the whale, you are missing radius 1 and radius 2. The big key here is once you recognize it's in equilibrium, where do you put the axis? In special rule, you can put the axis anywhere you want. Where do you place it where it can give you an advantage? Typically, you want to cancel out a force in terms of torque. In other words, give it 0 radius, and then you don't even have to put it in your table. Because question 3 is how many non-zero torques exist. Then you just sit at the table and just start filling in the blanks. The rest practically takes care of itself. All right, I'm going to end this here. Have a good day. This is Mr. M signing off.